All right, well, it's the last week of class, and so we should be pretty excited to be almost done with Math 240, and we'll just be tying up some of the topics we've been dealing with over the past couple weeks into more detail, and hopefully this will be helpful when you're studying, or more likely when you're watching this at 3 a.m. the day before the final. But either way, we have to cover a few loose ends about systems of differential equations. So last video, we talked about how to solve systems of differential equations when you had a non-defective matrix. So we have this set up, the derivative of x is equal to ax, and x is just a vector. So it's a system of equations that we have going on. And we said that if a is non-defective, then it's totally cool for us to write something out like this, where we have our solution being made up of exponentials to our eigenvalue, and then multiplied by our eigenvector. And as long as all these are, as long as this matrix is non-defective, we have a set of n linearly differential or linearly independent equations here that form our entire set. So we're good to go in that case. But now we need to talk about what happens if you have a defective matrix, because it's not as simple or even as literal as doing a non-defective case. All right, so the easiest way to do this is, again, just by example. So I have this matrix in front of me, which you can guess will be defective. But in any case, when we solve these systems of equations, we need to find the eigenvalues and the eigenvectors of this matrix. So you take the determinant of a minus lambda I to find eigenvalues and eigenvectors. And when I was doing this out in preparation, it's pretty ugly, so I'll spare you the details and just tell you. So we have lambda 1 is 2, and it has an algebraic multiplicity of 1. Great. And then our second eigenvalue is 0, and it has an algebraic multiplicity of 2. So we're fine here, right? We know we're going to be able to have one eigenvector, but we can get a little bit worried when we have an algebraic multiplicity of 2. So what we can do then is we can start off with the easy case here. So we take lambda 1 is 2, and we take a minus lambda 1I, which is a minus 2 times the identity, and that gives me 0, 2, negative 1, 2, negative 1, negative 1, and 2, 3, negative 3. So the algebra here is a bit tricky again, but I'll just tell you that your eigenvectors are going to live in the span of the vector 3, 2, 4. So even though this is the correct notation for writing the space of eigenvectors, you've never really seen me write it out like this before. But we're gonna consider the span of all of these for a very particular reason soon. So all of our eigenvectors look like 3, 2, 4 times some constant. All right, so then we have lambda 2 is equal to 0. So I have a minus lambda 2I, which just happens to be a. And so a was the matrix we have up here. And so my eigenvalues actually, well, let me actually go through and write it out. So a was 2, 2, negative 1, 2, 1, negative 1, 2, 3, negative 1. And so this is tricky to find the eigenvectors here. So what I can do is I can row reduce this, and when I row reduce it, which I obviously did with a calculator because I'm lazy, but we get this matrix here. And so we can examine it, and by rank nullity, we know n is equal to 3. My rank, I have 2 non-zero rows, so it's equal to 2. That tells me my nullity is equal to 1. And that's a problem, right? Because my nullity of this matrix tells me how many linearly independent eigenvectors I should be able to find. In this case, it's telling me I should only be able to find 1. And so let's go ahead and figure out what that is. Again, I'm writing it in this weird notation, but let's go ahead and make it 1, 0, 2. That works perfectly fine. And that's my entire eigenspace here. But remember, we said that our algebraic multiplicity was 2, yet we have a geometric multiplicity of 1, so A is defective. That's our conclusion here. And so if you take this approach that we did in the non-defective matrices here, and you try to write this equation out, what we get is that we have x is equal to c1e to the lambda 1, which was 2t, times our first eigenvector, which is in the span of this. So I might as well just call it 3, 2, 4. And then I have plus c2e to the lambda 2t, which was 0t, times my second eigenvector, 1, 0, 2. And then I run out of information. I have nothing else to do to tell me more about this solution. And that's a problem because we have a three-dimensional case, right? Because we're working with a 3 by 3 matrix here. So I need to find a third solution, but I have no way of finding it at this point. So what do? We have to use something called generalized eigenvectors. So what we're going to end up doing, this part here is going to be fine. This was a perfectly fine part of our matrix here and our solution that we're able to work with. But this part over here, we're going to have to redo this entire part to find our third solution. That's what this concept of generalized eigenvectors does for us. Okay, so what we're going to do is we're going to look for solutions of this form. I'm just going to call it x1 of t, just so we don't get confused with notation. But this is going to be e to the lambda t times v1, so an eigenvector. But then we're going to add onto it plus t times v naught. And so like this e to the lambda t v1 part is what we had written here. And then this additional t v naught is going to be what comes in this place here. But what's tricky here is that the v1 and the v naught are going to be a little bit more complicated to find than just going through and looking at eigenvectors right off the bat. Okay, so how do we find what v naught and v1 are? Well, v naught is just one specific eigenvector for that particular eigenvalue that's giving you trouble. So lambda equals 0 is giving us trouble. And so then just by definition, that means that a minus lambda I times v naught is going to give me 0. That's just a definition of an eigenvector, right? But we don't really know what v naught we should choose, right? So we have all of our v naughts are coming from a span of these vectors. And it's kind of telling us that we need to pick a particular one. So how do we figure out what v naught is going to be? Well, we use this equation here, that v naught is going to be a minus lambda I times v1. Okay, so that's going to tell us what our specific eigenvector v naught is going to be. But now you might think, what's this v1? How do we find that? So this is where things get a little weird, but v1 is what we call a generalized eigenvector. And so it's a little complicated how we find it. If you want more details, go to the textbook or the lecture notes. But pretty much we say, okay, I've run out of options to find vectors of this form, right? So what if I just do a minus lambda I square the matrix, and then I find those eigenvectors. V1 here is an eigenvector of your original matrix here squared. And then the only condition imposed on it is that it can't already be an eigenvector of the other one. What I mean by that is you can't already have it be in the span of your eigenspace for lambda equals 0. So what that means then is a minus lambda I times v1 cannot be equal to 0. Okay? So we have a few equations we wrote here. We have just the definition of an eigenvector, the definition of a generalized eigenvector, and then we have a couple conditions. I need to make sure that v1 is not already an eigenvector for A, and I need to make sure that v naught is going to be defined by this v1 here. All right. So this is what we're going to set out to do. And so our first step, because remember v naught comes from v1, is we need to find v1. So step 1, find v1. To do that, I need to take my matrix, subtract off lambda I from it, and then square it, which can be computationally difficult. So we do a minus lambda I squared. Thankfully for us, we at least have lambda equal to 0 So that just becomes a squared. But again, our matrix isn't super pretty, if you remember. So we have our work cut out for us, or at least Symbolab does. And so we end up with, when we square A, we get 6, 3, negative 3, 4, 2, negative 2, and 8, 4, negative 4. And if I multiply that by V1, I need to be getting 0, because that's just the definition, right? So you can look at it, you can just say, all right, well, I can pick a V1, and by looking at it, I can do 1, 0, 2. Because clearly that, when you multiply it by this matrix here, will give you 0. And so that satisfies this part here, right? That's great. But what you have to be really careful of is that this second part here, it can't already be an eigenvector for lambda equals 0. So if you go up to what our eigenspace was, we had the span of 1, 0, 2. So my eigenvector I picked out here, my generalized one, is already an eigenvector. So it's not good. I can't use this one here. That will run you into some trouble if you forget to check that point. So what you need to do is you need to pick a different one. So let's say there's other options, right? I can ignore the first column, and then I'll make it 0, 1, 1, right? Because that works perfectly fine as well. And that is clearly not in the span of 1, 0, 2. So this part is now satisfied as well, and I have my V1. So we're good to go here. After finding V1, we need to find V0. And so we find V0 just, again, by using this formula here. So I have V0 is equal to A minus lambda I times V1, which is, in our case, just A times V1. And if you do that out, you get exactly 1, 0, 2. So this is good, right? Because we know V0 needed to be an eigenvector of A, right? That's our definition here. So it's good that we got 1, 0, 2. But remember, we could also get 2, 0, 4, or negative 1, 0, negative 2. They just had to be in the span of this here, which is why I wrote it out in this way, just to remind you that they're not particular vectors, they're actually spaces of vectors. So they're, it's just kind of by coincidence that we popped out 1, 0, 2, as opposed to 2, 0, 4, or something else. But either way, we have our V1 and we have our V0, so we can construct our equation here. So we have x1 of t is e to the 0 t times v1 plus t v0. And so if we plug everything in, we get, I'm going to keep it e to the 0 t because I don't want you to forget that it's there. We get 0, 1, 1 plus t times 1, 0, 2. And when you put it all together, you get e to the 0 t, t, 1, 1 plus 2t. And what this covers then, this x1 of t, that covers both solutions here. That is this entire 2 solutions pretty much that covered lambda 2 is equal to 0. So when we put everything together, we have x of t is c1e to the 2t times our first eigenvector that we found, 3, 2, 4. So remember, no trouble there. And then plus c2 e to the 0 t, this vector we found here, t, 1, 1 plus 2t. And you can stick it all together if you want. I won't waste your time to do that. But yeah, this is how you do it here. And notice that just the presence of this t here makes it linearly independent. So I do actually have 2 solutions going on because of this t here associated with e to the 0 t. And the process by which we do it is, again, we just need to find these generalized eigenvectors here, and we need to make sure that we're picking our right original eigenvectors to go with so we can get our perfect solution going on. So this is just the case when we have trouble with one of the eigenvalues. If we have trouble with more eigenvalues, it gets more and more complicated. So I'll do that in the next video.